of Newton's first law. Come inside, I'll explain it to you.
Newton's first law states that objects in motion will stay in motion in a straight line at a constant speed unless acted upon by an outside net force, and objects at rest will stay at rest unless acted upon by an outside net force. When the car is moving initially, both the car and the books are traveling at a constant speed. However, when the car increases in velocity, the books have a tendency to remain at the previous velocity. This causes them to fall down in the back of the car.
Sophia, oh my god, are you okay? Why does my foot hurt? It's Newton's third law, don't you remember? No.
When Sophia kicks the rock super hard, she exerts a force on it. However, because of Newton's third law, every action has an equal and opposite reaction. The rock also exerts an equal force on her foot, which makes it hurt. The formula for force is F equals ma, and it shows how Sophia has the greater mass and smaller acceleration, and the rock has a smaller mass and greater acceleration, which produces an equal force.
Ah, you shocked me!
LOL.
Nothing's happening!
When Jess's sister rubs her socks on the carpet, the friction between the carpet and the socks leads to a separation of charges and the transfer of electrons from the carpet to the socks, giving the socks a charge. The excess negative charges repel one another and flow around the body because humans are conductors of charge. When Jamie touches Jess, the electrons are rapidly transferred through her hand to Jess, resulting in a shock because Jess provides an escape for the negative charges. However, when Jess rubs her feet on the tile flooring, there is not enough friction to create a separation of charges. As a result, the electrons are not looking for a way to escape as soon as possible, and Jamie is not shocked.
Oh, I see you finally got your license. I hate you, Sophia. Don't you know you need centripetal force to keep your keys in a circle? Why would you do this to me?
Newton's first law states that objects in motion will stay in motion at a constant speed in a straight line unless acted upon by an outside net force. In this case, the object is not moving in a straight line, meaning there must be some kind of outside net force acting on the object. This net force is called the centripetal force, which points toward the center and causes the object not to move in a straight line. In this case, the centripetal force is the force of the lanyard on the keys, which keeps the keys moving in a circle. However, when Bella lets the lanyard slip off of her finger, the lanyard is no longer acted upon by the force of her finger, so it no longer keeps the keys in centripetal motion. With no outside force, the keys fly off in a tangential straight line, hitting Sophia.
Hey, I got a delivery. Get to get it inside.
Hey Sophia, what's up?
The box won't move.
Oh, well, that's because of the force of friction pushing against you. Look, do you see how much friction there is on this ground right now? Come in, I'll explain it. There are two forces acting on the box in the vertical direction. The force of the earth on the box pointing downward and the force of the ground on the box pointing upward, which are equal and opposite as there is no acceleration up or down. In the horizontal direction, Sophia on the box is one of the forces pushing on the box. But there has to be another force acting on it for it to stay at rest because Newton's first law states that objects at rest must have an outside net force in order to move. Therefore, there must be some other force that counteracts the force of Sophia on the box because otherwise there would be a net force and acceleration. The other force is the force of friction due to the rough outdoor surface. Hey Bella, what's up?
You know, just dropping everything. But it's really weird because that bag's really heavy and that bag's really light, but they hit the ground at the same time.
Oh, that's because of Newton's second law. Come on, I'll explain it to you. Newton's second law states that the sum of the forces equals mass times acceleration. Therefore, acceleration equals the sum of the forces divided by the mass. The heavier object has a larger mass and is acted on by a greater force of Earth. The lighter object has a smaller mass and is acted on by a smaller force of Earth. When calculated, the ratios of the sum of the forces to the mass is equal in both objects, 9.8 meters per second squared. As a result, when the bags drop, they accelerate at the same rate and hit the ground at the same time. This is the law of universal gravitation.
was exhausting.
Are you okay?
I'm really out of breath, man.
That's because the gravitational potential energy got converted into kinetic energy too fast for you to be able to catch the ball. I'll explain it to you. The ball rolls down the hill because its gravitational potential energy is transformed into kinetic energy because energy is always conserved in a closed system. GPE is energy due to position. While at the top of the hill, the GPE is high, but the KE is low because KE is energy due to motion and the ball is stopped. However, once the ball begins rolling away when Jess clumsily lost control of it, the GPE decreases as it gets closer to the bottom and the KE increases as it accelerates. By the time the ball reaches the bottom of the hill, all of the energy is kinetic.
What just happened?
Projectiles travel independently in horizontal and vertical directions. The only vertical force that acts on them while they travel through the air is the force of the Earth. If you know how much time the projectile took to travel, you can find the vertical distance the projectile traveled using this equation. From that information, we can plug in the acceleration due to gravity, 9.8 meters per second squared, and the time it took for the pillow to hit Bella, and can find out how high up Sophia was when she threw the pillow.